Yeah, I'm gonna start with a very short introduction. I think everybody in this room wants to know the magnetic field in the corona, and I'm trying to suggest that we should consider using the Hall effect to measure it through measuring linear polarization, because linear polarization is readily measured in the solar corona because of the scattering regime we're in. And today, I'm going to try to make the case that the helium 1030 line might be a very viable way to move forward with pretty much the infrastructure we have today. So just to get everybody on the same page, the Hall effect is an atomic phenomenon that rotates and polarizes the linear polarization plane in the scattering geometry. So if in the case of just pure 90-degree scattering, as shown here on the left side, and these figures are from Javier Bueno's paper 2001. We only expect to see linear polarization in the 90-degree case scattering that's going to be parallel to the solar limb to observe. But if we have magnetic field present, as shown on the right-hand side, if the magnetic field is of an appropriate strength, that's very much a parameter of the atomic transition that we study, we're going to see actually slight rotation and depolarization of the linear polarization of the atomic transition. And if the magnetic field is too strong, as Sarah mentioned earlier today, we're going to have a so-called complete depolarization, where the actual change of the magnetic field is not going to tell us much about the strength or a longitudinal component. But what we're interested in is in the so-called unsaturated regime, where actually the linear polarization carries enough information to constrain longitudinal field definitely. And actually, the Hall effect was described for the first time 99 years ago in Wilhelm Halle's PhD in 1924. So maybe, hopefully by next year, for the 100th, might something useful in the coronavirus. Yeah. So just to show where we are in the landscape of magnetic field, like atomic physics, this the figure on the left over here shows us the different regimes that we work in terms of how much collisions matter and how strong is the magnetic field. So when the collisions remove a lot of the atomic polarization and we have strong enough field, we work in the Zeeman regime that are very used to see in our everyday solar physics like for example, HMI, NDI, and such. But in the case when the collisions are not very important and the magnetic field is the Larmor frequency is comparable to the the Einstein coefficient of transition, we get the Hall effect, which is this rotation of the linear polarization. Fortunately enough for us, the solar corona, I think, has magnetic fields on the order of 2 Gauss, which is the Hall strength for the helium 10H transition, which means that we can use if we can see the helium 10H30 transition in the corona, we should be able to use that to measure the magnetic field there. And there was a recent paper by Giulio Del Zana that was arguing that helium 10H30 should be extremely bright in the corona, made from very detailed atomic physics calculation. And even in that paper, they claimed that close to the sun, at typical coronal conditions, that 10H30 should be comparable to the iron 13 lines that we observe routinely with UCoMP. So that makes this line a great candidate to do this. I'm not the first one to come up with this idea. There's been like a very long series of papers in the literature, but I just want to point out one by Gabe that I think showed really nice how you can use combination of both forbidden magnetic dipole lines and the permitted 10H30 line to constrain the total, the full vector magnetic field in the corona. And I think in your paper, you from this eclipse observation 2006, they derive a field of the order of a Gauss, like 1 point.
Yeah, we had it. It was one of these like basically you can do something under a number of assumptions, which I personally come to believe unrealistic. One of them being the line of sight. So the paper was kind of theoretical. We in my view, you know, I wouldn't trust the result of the paper. But it's weird, least of all because the helium signal there, I believe, still to be primarily scattering or light that has been smeared from prominence emission. Like, I don't think that the signal, I don't think we had the sensitivity in that experiment to measure anything but light from prominences, and that was informed by it. So it was an eclipse. It was an eclipse experiment that actually happened before I was in grad school.
Yeah.
And then, so I wouldn't trust that result. The method has these caveats regarding where the location of the geometry is, but
I have a question from both of you. You're saying that some expectation is that the helium is as bright as the iron, so how low do you need to be? Because in the eclipse, you can go very low, you can see the speakers, you can see the ionosphere there, but I mean, in a chronograph, like UCoMP, do you expect the helium to be as strong as something we certainly don't see. So
The answer to this is this slide.
yeah, yes or no?
The answer is we don't need to see it low, we need to see it high if we're going to use it. Because you want it to be in the unsaturated high energy, which is on the order of a Gauss. But if you start looking at active, like more active sun in the radio, like what I'm showing here on the bottom slide, you start seeing magnetic fields that are 2 orders of magnitude higher than what UCoMP derives from wave tracking. So then, I mean, this is like a massive problem, like I feel like, because it's 2 orders of magnitude disparity between these different ways of measuring the magnetic field, right? And that's kind of a lot. It's not a factor to orders, right?
But how's the brightness wrapping up if I'm reading this? That's field and height,
Yes.
but the brightness for, to Juliana's question about the brightness that I'm using out there.
Oh, there's a paper by Jeff Kuhn that shows the brightness drop off, but I'm not sure. Like,
Just looking at our data, you don't see much helium emission.
I'll get back, yeah.
Above the filter, so.
Yeah.
If you could look lower down, like in the eclipse, I'm sure you would see more emission, but.
I'll get back to that as well in my talk. I have a slide later. Yeah, hello.
I have some comments and things regarding. So we all love Julio, but Phil Judge predicted those intensities in 1998. So the intensities in helium are comparable to the intensities in iron. They're pretty much very close. But the problem is that we don't know if that helium is actually coronal. So we can detect that helium at those intensities. The line should be strong enough. The problem is, and Gabe can say more about this, whether the line is actually coronal in nature or not, or you just see a very tight woven chromospheric structure that emits very brightly.
We can discuss this later, but like it doesn't really matter if it's coronal or not, as long as it's in the corona.
no, it does because is the helium at 1,000,000 degrees? Not. And Julie, I think Julie Lozano's papers to me seem to predict that you would see a signal of helium from a helium population at 1,000,000 degrees, and that signal would have a clear, broad. It would be much broader.
Yeah.
So a spectrograph would see it. That's why deepest observation will hopefully resolve. I personally will help solve it.
Yeah.
I have a really dumb question. Why would you expect to see helium? Why would its electrons not all be gone at 1,000,000 degrees?
It would just be a small enough fraction, but because
It's because
helium
we
is
have
there's so much helium
Okay.
present.
Yeah.
Basically, Lozano argued that they added some new atomic physics, that some form of recombination. There's many processes that are
Okay, yeah.
just so it's a dynamic. Basically, he's arguing that the equilibrium fraction is maybe high enough to see it. That is the paper that. And that's a good question to try to answer that, but it would be broad. I think that's how you could tell.
Can I come back to like
Yeah.
Jeff Kuhn's paper shows 1,000,000 degree, like if you compute the thermal width of the 1030 in his observations from 1999, like the eclipse.
The eclipse.
That line, if you compute the thermal width of it, is approximately 500,000 degrees.
The problem with that is that NASA tried to replicate this in subsequent eclipses and couldn't find it.
No, I don't know which.
What
which-
time in the solar cycle?
There was no other.
I don't know that one.
Because if those two eclipses were different times, it's all cycle.
They were different times, so it's 1999 to 2000 something.
That's for sure. I mean, it's, and it's. Agree to spend more stuff.
Yeah, but I just want to point out something that I think Sarah opened segue for it is like we have this massive disparity between the measurements in radio and other types of polarimetry and wave tracking. So I think it's really interesting to do a detailed analysis with forward and all the wave tracking methods to kind of reconcile the difference between the two and see what were the differences.
Well, one difference is the wave tracking is not sensitive to line of sight field, and a lot of the strong field could be carried, the energized field could be in the line of sight field, and it's not to be seen by the
All
latest
the time. I mean, statistically speaking, you know, and the field is mostly radial, and it should mostly be in the sky, but it's a good question.
It's not mostly radial. The field is all over the place. It's three-dimensional, even when
It's
it's
three-dimensional, exactly. So you wouldn't say, oh, the field has to be along the line of sight.
no, but there are shearing motions, and evolutionary motions that do drive preferentially along the line of sight. Some of the large scale,
Sometimes, sure.
well, no, throughout the solar cycle, the buildup of 4,000, for example.
So, you know, the problem is that if the field is anti-radial, you would lose all signatures. So in order to actually catch it, it needs to be vaguely close to radial. The deviation in the line of sight cannot be that big, or else you're going to lose it because of sensitivity issues. It's just geometry. So what you're seeing in the wave tracking is maybe an order of magnitude lower in the worst possible case scenario. So if you see 5 Gauss, it cannot be 50 Gauss. I would not say that. It might be 20 in total. So the problem that Momo says is real and it exists. It's there.
But prominences have been measured with tens of Gauss, 50 Gauss. So there are strong fields up there. They're just not going to be what
The
critical.
problem is that radio gives us 1000 Gauss or
But
600
it's
Gauss.
below, it's a totally different radial height than what we're looking at. We're looking at 1.05 and above. They're looking at 1.04. So yeah, the field changes radically, but it drops off.
Yeah, right there. Yeah, what's up? Was there?
Richard Martin.
What's that? Richard, go ahead, Richard.
Hi, I'm just wondering which radio measurements you're talking about. Is it the ones from like the Fleischmann group?
There are multiple, like in this review paper by Fedenev and that Gregory is on it as well. They have a collection of many different ones across the last solar cycles. It's not just his group.
I thought they were from sort of intense active regions where there was really strong flaring going on, which might, explain the difference. Most of the comp observations are in sort of quiet sun. I mean, it does cross the active regions occasionally, but the very specific events that the Fleischmann group is kind of looking at, I think, which is where they get the really strong signals. That's what I had thought anyway.
Good point.
So it's low down and it's strong active
Yeah.
regions.
Okay.
Okay, sure, we can talk about it, but this is not the main point of the story. It's just something that I get. Okay, I'm gonna keep going. So with Roberto, I've been working on extending previous range transfer code that includes enough. So it includes a lot of atomic physics. And it can treat fully the unsaturated Crowley regime. So what I've been working on is extending this this code to accept more realistic coronal magnetic field configurations. And in this talk, I'm going to present, for example, my recent work where I actually included a twisted flux rope in the corona. And that's shown down here. It's pretty simple. It's like a slinky. It's like a magnetic slinky that I put in the corona. And I've just been looking through how it looks like in 1030, if we can actually observe it. So the observing geometry is the following. We're observing a flux rope that's in the equator, and we're observing it at 90 degrees. So pretty much like edge on. And what we can see for the two different toroidal magnetic fields configurations, in this case, the axial field is 1 Gauss, So we keep the 10-830, the unsaturated regime, and I integrate it along the whole domain. And how I define the Q and U in this case are the reference frame is radially defined for every point. So pretty much like Q and U, like the reference frame is rotating as we rotate along the sun. So if there was no highlight effect at play, we're only going to get Stokes Q, no U. But we can see that. If you don't have any magnetic field, you're not going to have any U. It's just going to full Stokes Q. But because of the magnetic field, we see this really complicated pattern in the U, and this is what an observer on Earth is going to see. And the difference between the two configurations when the toroidal field is pointing in and out is shown on the third row. So pretty much in this configuration, what we're seeing is if we integrate the whole line, the change in Stokes V will be on the order of like 10 to the -5. But the change in U is going to be on the order of 2%. So this is more easy to measure than Stokes V. And this is extending the work by Gabe, where they only had like and other work by others, but they only had like a plane of the sky setup. This is like a full like integration of the whole domain, which is very it's very reassuring that if we can observe this line, actually, I think this might work.
Can I ask a quick question if you go back? Can you tell me on those plots below here, this is the view, you're looking at it in quadrature, right?
Yes.
So where is the axis of the flux rope in these figures?
It's it's at 1.5. And
So, okay, so it's like where you're seeing that little coming together point.
Yes.
Just wanted to make it.
Yes. And you can see how like the U flip signs between the two. So yeah, in order to really interpret this, you're gonna have to know a lot more information than just having the 10-830 observations. Like you're gonna have to know that you have some sort of a cavity with a flux rope system before you observe it. But if you know what's there, this is a clear signature of the longitudinal
That
field.
would be like a prominence and show that in the.
Yeah.
And the other thing is that if you know that it's directly along the line of sight, that azimuth, you just take the arctangent of that azimuth and it'll tell you the field strength. Quantitative.
Yes.
Gives you that number because that simplifies in that case.
I haven't looked into that yet because there's a few other things I need to. Yes, but yeah, that's the next step because right now there's like a lot of moving parts in this model, and I can do that. Yes. So it's the pathological case of the Hana effect is when you have the flux rope in the plane of the sky at 90 degrees. In that case, you can only tell the chirality of the flux rope, but you can't tell the direction of the toroidal field, which is kind of bad, but we already knew that. Like Roberto has a paper about it from like 20 years ago. So that's known. But as long as we have some sort of flux rope that's not in the plane of the sky, we get different Stokes U's for every single different case. And in this case, I'm just showing you the resulting Stokes Q, the Stokes profile for 10-830 for this orientation of the flux rope. And the model differences for the two different combinations of chirality and direction of the toroidal field are shown, I think, in this figure is really complicated. Well, the moral of the story is that we have different patterns for every single different configuration of the field. So it seems like it's working, which is nice. And also the differences in the Stokes U are on the order of like a few %, which is an easily measurable quantity, more easily measurable quantity than the integrated V signals, at least in this configuration. So this brought me to UCoMP because UCoMP can observe 10-830. So I was very interested. I was like, oh, can we use UCoMP to do that? And I literally downloaded the first day, the first day I found, and there's actually a prominence eruption. I was like, oh, that's amazing. So this is the IQ and U level 2 data, raw data that I downloaded. And you can see all these background like stuff that's there. So I went along and I like subtracted that, like I rotated the patterns to be vertical, and I subtract like averaged and remove the background and all this neat stuff. And what I got was the following. I was able to compute the azimuth and the linear polarization from the Q and U. And when you compare this with AIA, like on the right, you can kind of see that the emission between the two kind of seems similar. And then when I computed the, you can think of it as deviation from the local radial azimuth. I found that the two regions that kind of hit like the two, I'm gonna, my cursor is not appearing, but the directions where there are two active regions, one of them is kind of in the bluish part of the wheel, of the color wheel, and the other one is kind of toward the orange red. So once you start looking at the deviation of the reference, like the angle of the deviation of the azimuth from the local radial direction, you see that kind of these two regions kind of see to deviate from the one-to-one line, which was kind of interesting. I was like, oh, is this a 100 rotation signature? Because if we are actually detecting, planetary there, and we believe that the magnetic field measurements of the coronal magnetic field at this region, this means that these measurements should be highly sensitive, right? But then I went back to the comp team, and they were like, no, the background was subtracted. So I read the analysis of subtracted background, and I got this. It's kind of a bit more disappointing.
Yeah. So can I ask, so are you showing in the plot from before, or are you showing the radial azimuth?
So this is a radial azimuth versus local radial. No, sorry. Yeah, this is azimuth. The azimuth computed from the QNU versus the local azimuth. So basically, if you have a deviation from that, that should be 100.
Right, but have you made the plot where you're showing, you take the UCoMP data and get the radial azimuth, so that would be the look, so you don't have to worry about color wheels at all.
Yes.
The departure from the local radial.
Oh no, I haven't done that.
Yeah, because that's
I haven't done that.
the easy way to see if it pops out as having a deflection, because otherwise you have to subtract the color wheel in your head, which makes my eyes drop.
Okay. Yes. So I go like after the subtracted background, the thunder disappeared from the stock. But I think there's something to be learned from the background subtraction, is what I'm trying to say here. And I still want to work a little bit more on that, because if there's actually like extended 1030 emission and we subtract it with the background estimate, I think we might losing the signal thereafter. And actually something really neat that came out of this day, like I was so lucky, this was the first day I downloaded from the server. There was like a prominence eruption that you're gonna see right here. It's happening, and a little bit later, you can kind of see it over here in this 171 too. And you can see the prominence material lifting off. This is the UCoMP observations, and this is linear polarization. So this is actually linear polarization detected in the prominence material. So the question is, at what point does the prominence material become obtain a magnetic field strengths that are compatible with the unsaturated Halley regimes? And that's not very clear to me. That's a question that I'm still working to figure out from modeling. So I think this work has a lot of future prospects. The first thing is, where is there actually helium to be observed in the corona? So Roberto volunteered to do the PI of this experiment called the Coronal Helium Emission Spectrograph Experiment, aka CHEESE, that we're building right now. And you can see it, like it's going to be a very simple spectrograph, but we already have the diffraction grading and a bunch of other parts, and we're moving towards assembling it. The design part is over. And I really want to thank Roberto for guiding me through the whole process of building an instrument, because I haven't held a wrench in a long time. Yeah, but to get back to the UCoMP data, like I think we can place an upper bound over. Yeah, no, oh, sorry. We can place we can place an upper bound of how sensitive 1080 is in the corona by using the data that we have. And I really have to push forward, and I'm supposed to do it in the next few afternoons, is like figure out how the background subtraction works and how reliable it is, because this would be a pretty much an observational constraint to all these papers that we're discussing, like all these numerical papers. That's a way forward. And another thing that I'm really interested in is to really incorporate NHG models in the scattering polarization code that we have with Roberto, well, it's mostly Roberto's code, to compute the resulting Halley effect polarization through a realistic eruption. And why I'm saying this is because, like, when you have a realistic magnetic eruption on the sun, the plasma contains many different components. So they have different temperatures and they have different ionization states and just different thermodynamic states. So computing the contribution for each one of them would be very important to understand what we can, which parts of an eruption, if we observe, are actually going to be in the unsaturated Halley regime. And how would it be better to design an instrument or design an observational program to make this measurement? And the one thing that I'm really excited about is if you look at these 3 or 4 images from Solar Orbiter, you see the prominence material to like a few solar radii. So I think the signal in the 3 or 4 is not so far away from, like, what I'm trying to say is if there's prominence material, the cool prominence material in 3 or 4, I think we should be able to see it in 10 and 30 really far away from the sun, which would be pretty crucial for like actually trying to figure out what BZ is from ICMEs. So I'm pretty excited about the last prospect for that. And that's not my last time. Oh yeah.
So are you now thinking about that?
2 questions. Go ahead, please.
Yeah, are you now talking about the 2030 atmospheric temperature, or are you talking still about this change?
I think it's
So
more
what
about,
we're
it's talking about the cooler environment.
Are you now talking about the cooler?
It doesn't matter.
Yes, doesn't matter. Let's see what we can get. Maybe we get only the atmospheric one, maybe we can get the diffused one. Maybe we can get both.
The design of the instrument that you're having, right?
Sure. Yes. Yes.
The main problem with UCoMP is that we don't have a true continuum or a good continuum to subtract to either. That's just the way the instrument is designed, because we don't have a choice on how to move our continuous measurement. This is a fixed distance from the line peak, so you don't have a continuum period.
I agree.
So I think a good design, if you want to go after that, you really need to have an instrument that can give you a reliable instrument of the continuum to subtract to your line. You want more point across the line.
Yeah.
I don't think it was sufficient for a line like Helium. This can be done with UCoMP. It's really bad.
Very
Real
quick.
subtraction.
Very quick.
Wait, can I come back?
Yes.
Okay, then, you're gonna have to wait.
Yeah, well, Julian, you're making a really good point, and I feel like the chip instrument was an amazing precursor for that, because it was showing up to its field of view, like it was showing the 10 and 30 beautifully. So it's going to have calorimetry in it.
It had the same, well, we didn't measure continuum.
We didn't measure continuum,
But
we didn't do polarimetry. That was the only had the line just high.
Yes.
So that was basically only the code was measured by velocity.
Mhm.
There was no polarimetry there.
So let's say, one more, go ahead.